So we were at this point. We were at we had just discussed homolytic fission, heterolytic fission. What's a free radical? What's a nucleophile? And what's electrophile? TK Sara. This was discussed, and we started talking about the physical properties of alkanes, which were that they were saturated hydrocarbons. TK, no idea why this. So they were saturated hydrocarbons, which meant that they had carbon and hydrogen atoms only and single bonds. TK, just hold on 1 second. So just carbon and hydrogen atom, they had low melting and boiling points because they only had van der Waals forces, which were weak intermolecular forces. Instantaneous dipoles, induced dipoles, they were non-polar inherently, and they wouldn't attract each other very strongly. So most of them were gases, low melting and boiling points, but the melting and boiling points would increase with size due to the greater van der Waals forces. Not soluble. They were not soluble in polar liquids like H2O because I told you that water molecules, they're very polar. So they're not going to attract alkanes. But remember, alkanes will dissolve in non-polar solvents. Alkanes will dissolve in non-polar solvents. I mean, the rule for solubility is that polar dissolves polar and non-polar dissolves non-polar. That's a rule because polar things will only attract other polar molecules. So non-polar things would only mix with. I said they would, and the rest of the properties. So we had started talking about reactions of alkanes, which was, I told you that they were unreactive. They were non-polar, which is why they don't. It's a non-polar molecule that doesn't attract other molecules. So the inherent non-polarness of this molecule is not. It's going to make it very unreactive. The other things, so the first reaction and probably the only reaction that we're going to discuss is free radical substitution, where you have Cl2 or Br2 in UV light, they're going to react. And what's going to happen is that one of the H or multiple H's would get substituted by Cl atoms. And it could be any Cl atom, like many H atoms might get substituted during this reaction.
Sir?
Yes.
You know how you said that alkanes are unreactive because they're non-polar. Does that mean they only have van der Waals forces?
Yes, they are. They do have van der Waals forces. This is what we discussed. They've got weak because they're non-polar. They only have van der Waals forces. There are no dipoles. Carbon and hydrogen atoms are they almost have the same electronegativity. TK, which is mentioned over here. Is that clear?
Yes, sir. Thank you.
So mechanism of this reaction, of this specific reaction, of this substitution reaction, 3 steps: initiation, propagation, and termination. So initiation, we're going to start with initiation. It's the step where free radicals are formed. So we're going to do the first one first. So just remember what initiation is. What's going to happen is that due to specifically UV light, the Cl2 molecule, its bonds, they break homolytically. There's going to be homolytic fission, which means that so this one is homolytic fission. And this happens because of UV light, because of ultraviolet light or sunlight. The bonds are going to break and it's going to produce 2 free radicals are produced. Both of them have unpaired electrons. So free radicals are formed. That's the very first step. The next thing that's going to happen is, that's the first step, free radicals are formed. It's because of these very reactive free radicals, which are very reactive. So we can write that down, because their bonds are incomplete. Remember, chlorine is also very electronegative, so it wants to gain electrons from somewhere. So it's going to try and pull electrons from other atoms. It's going to try and do that. So which is why it's going to be very reactive. So we're going to move towards the propagation step. In the propagation step, the total number of free radicals that kind of remain the same. So propagation, total free radicals are the same. So here's a molecule of ethane. Let's do this for ethane. And the Cl radical is going to try and gain electrons. It's I mean, there are 2 electrons over here. So what would happen is that the Cl radical will try and pull the hydrogen atom's electron towards itself, and it's going to try and bond with it. Because the Cl is looking for an electron, it needs 1 electron. So it's going to try and pull the electron from the hydrogen atom. So a hydrogen atom, instead of bonding with the carbon atom over here, it's going to move its electron and withdraw its electron and give it to Cl. And the carbon's electron goes back. So the product is going to be an ethyl radical, because now carbon, it doesn't have a complete outer shell. It's, I mean, one of its electrons is now not bonded to anything. So and the HCl molecule is produced. So this results in the formation of an ethyl radical. Is this clear, everyone? Yes or no? Is this clear? Anna, is this clear? Abdullah?
So is radical just a fancy word for atom?
It is not a fancy word for just an atom. I mean, over here, Cl is just an atom. TK, that's right. But radical is something whose outer shells are not complete. It's something with unpaired orbitals. Like carbon over here carbon has a total of 4 orbitals in its outer shell, right? I mean, 2s1, 2px1. I mean, it's got 4 electrons basically. And 2pz1, right? So the thing over here is, look at this carbon atom over here. It got 1 electron from hydrogen, 1 from another carbon, 1 from another hydrogen. So it got electrons in these orbitals, but one of its orbital is incomplete. It's unpaired. So that's the dot over here. Is that clear?
Yes, sir.
So it could be a molecule as well, which has unpaired outer shell electrons, which basically means it's got empty orbitals, not completely empty orbitals, half-filled orbitals. So this carbon is full. I mean, the one on the left is not a radical. It's got 4 electrons. All of its 4 orbitals are completely full. This one, all of its 4 orbitals are not completely full. This one needs electrons. So you've got so this one is your ethyl radical now. TK, something that has unpaired electrons. TK, we wrote down the definition for that as well somewhere. Okay. A free radical is a reactive species which has unpaired orbitals or electrons. So methyl or chlorine or any molecule that has that particular property. Okay, anyway, so you've got this first step number 1. Now you have an ethyl radical at your hand. That's very reactive because carbon is short of a bond. So carbon will try to gain electrons from somewhere. So at the moment, carbon is short of 1 electron. So if it sees a Cl2 molecule, What it's going to try and do is it's going to try and bond with that Cl. It's going to try and pull that electron away from, bring that Cl close to it, and will try to bond with it. The other electron goes back to this Cl. So this is what's going to happen now. The ethyl radical is, one second. So your ethyl radical now has a Cl atom that's bonded to it. And as a result, another Cl radical is produced. So another Cl radical is produced because, this Cl atom got pulled towards this carbon. It started sharing its electrons with this carbon over here, ended up bonding with this, and the other Cl atom is now left all alone. So that is now a free radical. So these are your two steps that are going to happen whenever there's going to be free radical substitution and whenever there's going to be a propagation reaction. So are the two steps clear for propagation? The first step is, let me just revise. Cl radicals were produced in the first step. Because of UV light, you got these very reactive Cl atoms. They went, pulled the hydrogen atoms away from the entire molecule, joined with them and turned into HCl. And the carbon atom was short of one bond, so it became a radical. Now the carbon atom would want one of its electrons back. So it's going to try and pull a Cl atom from a Cl molecule, Cl2 molecule, bond with it, and the Cl radical is produced again. So is this clear, the two steps?
Yes, sir.
Okay, Hania, is this clear?
Yes, sir.
Okay. Now the thing is, the same two steps are just going to repeat over and over again. What's going to happen is, what's going to be different is, let me just. So the two steps are going to, the propagation steps, they just keep on happening randomly. The only difference would now be that you're going to start at this position. One of the Cl has already been substituted. So your starting molecule over here, initially your starting molecule had all of them were hydrogen atoms, right? But now your starting molecule repeat the same exact step, except that now the starting molecule will have one Cl. So I'm going to just repeat everything except that the starting molecule now already has one Cl that's already substituted. So I'm going to put in the Cl over there. Okay, and put that Cl everywhere because there's one Cl that's already in the previous step, it joined the carbon chain.
So I don't understand. What did you just do?
I just repeated the whole step except that what I was saying was, the first two steps are going to repeat. Like the Cl radical would come in and would try to steal one of the H atoms, right? So when we ended the two steps, we were at the same point. You got a Cl radical, you had the same molecule, except that one of the H was already substituted. So the Cl radical would come in and it's going to now do the same thing with some other hydrogen atom. Hani, do you get this point?
Yep.
So it's exactly the same step, except that there's one Cl already there because one Cl already got substituted, right? So one Cl is already substituted. Now all you have to do is you have to repeat the whole thing again, but now with a different hydrogen atoms. Remember, you have 6 hydrogen atoms. One of the Cl has already been substituted. So the Cl radical would start all over again, but now with some other hydrogen atom, and one Cl is already there. So is this clear? Alicia, clear? Mayim, is this clear? Zari?
Yes, sir.
And you can keep on repeating these steps. So now you have 2 Cls over here. So just repeat the entire step. What's going to happen is Same thing. Okay, so the propagation step would just continue endlessly. So now my starting point is that 2 CLs have already been substituted. So my starting point is that I already have 2 CLs over here. So already got 2 CLs into the molecule. And now I have a third CL. So my starting point was 2 CLs are already part of the molecule. Now the Cl radical is coming again and it's attacking some other hydrogen atom. So pulls that H atom away, HCl is formed, that turns into a radical, that radical goes to a Cl2 molecule, pulls a Cl and joins with it. And now we've got 3 Cls. So it's going to eventually continue. So it just continues randomly until eventually you either run out of Cl atoms or Cl radicals, or at the end of the day, all of the hydrogen atoms are gone. Okay, all of them would eventually be gone. So that's basically your propagation step that's happening over and over again. But it's the same step repeating over and over again. So hopefully this is all clear. ठीक है, कोई issue तो नहीं, any issues? Maim all fine, Nabila, Rubab. Hania, is this clear?
Yes, sir.
ठीक है. So the last one. The last step is known as your termination step. Now, these steps are not, I mean, the first one was initiation, that happens. That is when the reaction starts. But these other steps are in no particular order. They're just randomly happening. So this one, termination, what is the termination step? Termination is then free radicals get used up. They get used up. So for example, you had all these free radicals getting formed, right? I mean, look at this free radical. This free radical was formed in, I mean, some propagation step, it got formed. So I'm going to just copy this free radical. Anyways, that's not an ethyl radical anymore. It's a dichloroethyl radical. Like it's got 2 chlorines as well. So I'm just going to delete this. It's not just an ethyl radical. It's an ethyl radical with 2 chlorines. So this one. I'm going to copy this radical, paste it here. So we have a number of radicals. Remember, the reaction is happening haphazardly. There are a number of radicals getting produced. And you can see there's a Cl radical getting produced. So you can pick the Cl radical. And you can have it here. So this carbon needs 1 bond and this chlorine also needs 1 bond. So why don't they just bond with each other? So why don't 2 radicals simply add up? Why don't they just combine? So that's what's going to happen. You'll have a carbon. This one is HCl. There's going to be another Cl attached over here. You'll have NH and NH and a Cl over here. So that is what termination is. 2 free radicals react to any of the 2 free radicals. Any 2 free radicals in any of the previous steps. They might get in touch with each other and they might just, I mean, both of them are looking for bonds. So any 2 free radicals they are going to combine. And it could be literally any 2 free radicals. So you can have a number of free radicals formed. So you could have this free radical. like any of the H atoms might get substituted. And they could be so they're both looking for bonds. So they're just going to combine together and they're going to react together. And this one would be, I mean, you have Cl, you have another Cl, and an H, another H, and this would be H, H, and Cl. You could have used a condensed form version of this as well, but this is what's going on. That any two random free radicals, all the free radicals that that were getting produced over here, all of them in all these multiple steps. I mean, this free radical could combine with some other free radical like this one. They can get together. So any of the two free radicals can simply join up, and you'll get these different compounds. Is this clear?
Yes,
So,
sir.
so just any two random free radicals. Now, the thing that you should notice over here is that most of the free radicals that you're getting are either Cl radicals or they are chlorine substituted free radicals of this molecule, like ethane. I mean, where's the original molecule? That's the original molecule. Ethane losing its hydrogen. So it's going to be a version of a 2 carbon atom radical. It's going to be, I mean, this H would be gone, so it would turn into a free radical, or Cls might get substituted and it would then turn into a free radical. So most of the free radicals that you're forming in the process are some version of the original molecule. And it could be either of the 2 carbon atoms. Either this could be a free radical or this could be a free radical. So if I do this, if I do the last step, let's say I do it with butane, right? Now butane is going to have many steps. So let's do butane plus Br2 plus UV light. Remember, it has to be UV light, otherwise there's not going to be any free radical substitution. As anyway, so I mean, the first step would be initiation. So initiation. So that's initiation. That's simple. Bromine radicals are going to be produced. You'll have 1 Br. Electron goes back. This electron goes back. Homolytic fission happens. And you get a Br radical. And you get another Br radical. Next is propagation. The propagation step just randomly continues. You can't draw all the propagation steps, but you just have to know what the basic idea of what's happening in a propagation step. Like you'll have a butane molecule with all its many hydrogen atoms. It's got lots of hydrogen atoms. And remember, the Br radical is going to come along and it's going to try and steal any of the hydrogen atoms. So for example, the Br radical comes along. It sees this hydrogen atom, tries to pull it and tries to bond with it. And this carbon gets its electrons back. So remember, it could be like the Br radical, like in the previous step. In the previous step, we had a Cl radical coming along, right? So, I mean, it could steal any of the hydrogen atoms, any of them. and the molecule would turn into a radical, and Cl would get its hydrogen atom. So the same thing kind of happens over here. You've got butane, and the bromine molecule can target any of the hydrogen atoms. So if it steals this hydrogen atom, what's going to happen? It's going to turn into what? It's going to turn into a butyl radical, but except for one thing, which is that all these hydrogen atoms are there, except for one of the hydrogen atoms is now missing. This one. So this carbon is now a radical, and an HBr molecule is going to be produced as a result. So just remember, any of the radicals could be like any carbon atom could become a radical. It's not just the end one or this one. It could be any carbon atom. Is that point clear? You clear, Sarko, Rabab? Is this clear? Nabila, Mayim, Hania, Abdullah, is this clear?
So could you just explain it one more time, please?
This one? Yeah, just a second. What I was suggesting was that in the ethane molecule, I showed you that a Cl radical came along. It wanted its bonds back. It wanted an electron from someone, right? So it saw an ethane molecule and stole one of the hydrogen atoms and made HCl. Hani, is that clear?
Yes, sir.
So my only point is that the Cl radical can select any of the hydrogen atoms. It could steal any of the hydrogen atoms. I mean, that's the whole point. So when I drew this butane molecule, just a second. So when I drew this butane molecule, that was the point. That, I mean, this time I'm not using Cl2, I'm using Br2, but it's the same thing. Br radicals coming in. So my point was that it could steal any of the hydrogen atoms, not just the one at the end, but it could be the ones in the middle as well. So it can steal those hydrogen atoms, take the electrons and bond with them and form HBr. And the carbon in the middle would lose its H, so it would turn into a radical. Is that clear?
Yes, sir. Thank you.
Yes, sir.
And the next process would be exactly the same. It could be the same thing that, I mean, this molecule, I'll just copy this. So you'll have this.
So when we draw this radical thing, do we just draw a dot? Like we don't need to put Br over there?
Over here?
Yeah.
You'll put a dot because the Br stole its hydrogen. It went away, like the Br came and just took the hydrogen away. Is that
I
clear?
just understood. Yeah, thank you.
So the Br just came in, stole it formed HBr. And the next part was that, I mean, the carbon needs its electrons back. So it's going to attack a bromine molecule. And it's going to kind of do the same thing. Like it's going to see the bromine atom and it will try and pull the electrons of the bromine atom and bond with it, right? And the other bromine atom would just go away. So what's going to happen is that so this bromine over here is going to take its electrons and bond with this. Let's rub the other things. It's going to take its electrons, one of its electrons, and simply bond with this carbon atom. So carbon's bonds are now complete. Now this is a free radical, which is Br now. That's your free radical. That's going to be produced. Okay, let's keep it there. So is this clear? All clear? Yes or no? Sorry, is this clear? Anna, Alicia?
Yes, sir.
Yes, sir.
So now the final thing is that, I mean, this was the only thing I wanted to tell you was that the free radicals that are getting formed could be any carbon atom could be turning into a free radical. So what we're going to try and do is, just one second. So what we're going to try and do is, okay, I'm going to draw a random molecule. Let's say I have this molecule. Let's say it's this one, and it has all these hydrogen atoms, lots of them. So it's a slightly more complicated molecule compared to the previous one. Now, the point I'm trying to make is predict how many different types of free radicals could be formed. There could be a lot. Remember, the carbon-carbon bond never breaks. Make sure you note this. Like over here even, I mean, the Br radical is attacking this molecule, but it's only attacking the hydrogen atoms on the outside. I mean, the carbon chain never breaks during the process. It never breaks. It actually increases in size during the termination step. Like over here, you had a 2 carbon atom free radical, you had another 2 carbon atom free radical. So the carbon chain would increase in length, but the carbon chain would never break during the process. Is that clear? This thing? Yes or no? Is this clear?
Yes.
Okay, nothing is happening to the carbon chain. Okay, Abdullah, is this clear? Okay, the carbon chain stays.
Yes, sir.
The
Yeah,
carbon
it does not break.
It does not break. It stays intact. Okay, it's only the outer hydrogen atoms that are continuously lost. So I'm just going to try and draw the different types of free radicals that are possible during this reaction. So, for example, here's one. So you could have a number of free radicals that could be formed. Like the H goes missing over here, Br takes it, and it turns into a free radical, right? Or what else could you have? You could have. So how many different types of free radicals are possible? So the Br attacks it and takes away an H from some other place. Let's say this one. So this carbon over here turns into a free radical, right? So this carbon over here could turn into a free radical, or what you could have is same molecule. Br comes along and steals this hydrogen over here, and this hydrogen turns into a free radical. Or it could be, I mean, it's important that you should be able to differentiate different structures. There could be another one, which is this one. So there could be another one, which is this one, that the H atom is lost on this carbon atom. Now, the point I'm trying to make is, if I just color these carbon atoms with a different, let's make it red. Just one second, let me. And we have this one. So anyways, I mean, your knowledge of different structures, like you can have this molecule can turn into these many different types of free radicals, right? Could there be any other possible free radical? Is that possible? Like it could be this carbon atom. Remember, focus on this thing. This carbon atom and this carbon atom are exactly the same. Like they're bonded to the same. I mean, these two are exactly the same. Like there's a CH3 and there's another CH3 and they're bonded to the same carbon atom. So if I make this the free radical or make this the free radical, it's kind of the same thing. Is that point clear?
Yes.
Yes, sir.
TK, is that clear? Hani, is this clear? Anna? Mariam, is this clear? Okay, these two are exactly kind of exactly the same. TK, they're exactly the same structure because they're bonded or they're branch structures that belong to the same carbon atom. So which is why I'm not making this a free radical, because making this one or this one, it's kind of the same thing. TK. What I can do is I can actually show this. Just a second. So if I had, instead of that, made this the free radical. And this was my normal carbon atom, right? These two are exactly the same. No difference whatsoever. So these two are exactly the same because this carbon atom, there's a branch and that's a free radical. This carbon, there's a branch and that's a free radical. Okay, so it's two branches coming from the same carbon atom. I said, but anyways, you must have an idea of how many different possible radicals are possible. Okay. Remember, this end and this end are different because the methyl group is further away. Over here, the methyl group is right next door. The middle two carbon atoms are different because one of them has a methyl group attached. The other one doesn't have a methyl group attached. So I mean, these two carbon atoms and these two carbon, the two carbon atoms are inherently different. So you'll have all these free radicals. And then there's going to be a number of different variants of these free radicals. Like I told you that during the propagation step. So I also told you that during the propagation step, the CLs would continuously get substituted. Like you'll have a radical and every time it's the same reaction, except that there are more and more CLs in the molecule. So the same thing would happen. That you'll have all these free radicals getting formed, and every time there's a reaction, there's a propagation step, one of the H atom gets substituted by a Cl atom. So the molecule will have more and more Cl atoms or Br atoms, depending what you're reacting it with. So there would be different versions of these radicals. Every time there's going to be a Cl atom that's going to get substituted. TK, maybe this time this. So the propagation step just randomly continues. Every time there's going to be Cl radicals getting substituted in the reaction. So is this clear, everyone?
Yes, sir.
Okay, so just remember that how many. Now there've been some very tricky questions, but is this clear? I mean, I need to make sure that this is 100% clear. Hania, is this clear? Abdullah, is this clear?
Yes, sir.
Okay. So there've been a number of questions on this. Like for example, they might give you a question where, so there was this one tricky question where they stated that and they were very specific in the question. They were specific in the sense that they were just talking about monochloro substitution. I mean, they often use this word. Remember, we're talking about free radical substitution. Monochloro substitution means just one Cl getting substituted. Okay, that's Just one Cl atom. So the question was, just one second. I said just one Cl atom getting substituted. And they were asking for monochloro substitution of propane. And they were saying I said now they were saying that if monochloro substitution happens, you get two types of molecules. One of them is this one. You get one chloropropane. So all the H atoms are there. And one of the H atom gets substituted by a Cl. And the other one was that you had two chloropropane, which was that you had the same thing. And this time all the other H atoms are there. And they were asking, let's draw the H atoms. So I'm just going to end it here. We're going to discuss this question in the next class then. And the question was, what is the probability of getting this one compared to this one? Like, what's the relative probability? Like, out of 10, how many of these molecules would be produced and how many molecules of this would be produced if there's one chlorine that's getting substituted? So you had to figure out what the probability was. So I think we'll discuss this question in the next class then. But try and revise this and make sure you understand this completely, okay? So let's continue next time. Any questions? No questions? Chale. Let's continue tomorrow then. Okay, everyone, take care.
Allah
Allah
Hafiz.
Hafiz.
Allah Hafiz.